morning all. So today we are going to discuss about the synchronous detector, what we have discussed in the last class. In that some additional features are there that we are going to discuss in this class. Okay. So step by step we will follow. So first, last class we have discussed about synchronous detector. Now in synchronous detector we have seen that it is we are synchronizing the carrier frequency, what we are going to transmit and what we are going to receive. So while transmission we require a carrier which carries our information after modulation, and then power amplifier is provided. That modulated signal is provided to the power amplifier, and then it is transmitted through a particular channel. Now this synchronous detection, what we have discussed in the last class, that according to the principle of this synchronization, the word synchronization itself indicates that we are matching the same carrier frequency what we are transmitting at the transmitter end and what we are using at a demodulation, that is also same carrier strength must be available. Last class I have drawn a block diagram that suppose this is the transmitter end and this is the receiver end. Okay, this is transmitter part, this is receiver part. Here we are transmitting the AM signal, here we are receiving the AM signal. Now this is the transmitting antenna, this is the receiving antenna. In this modulation takes place, and in this demodulation takes place. Now modulation means change the characteristics of carrier component, and demodulation means extraction of the original message component from the received modulated signal. Now here ideal case what we are seeing, in demodulation, the certain block diagram we have drawn that there is a mixer after reception of AM signal. It is provided to the mixer in which the local oscillator signal is provided. It will provide the carrier signal. Okay, it will provide carrier signal followed by an LPA. Okay, so followed by an LPA, and then we can reconstruct the modulating signal. So this is the small block diagram what we have discussed in the last class or in previous class, that in modulation we are using a carrier frequency. If the same carrier frequency is used here, if the same carrier is used to demodulate the received AM modulated signal, then we will say it is called synchronous or it is called coherent detection. Okay, but that too, here we are using cos omega ct, and at transmitter end we are using, this is the mixer followed by a band pass filter. Then this band pass filter output is provided. So this is my message component M of t. This is my carrier component A cos omega ct, and this whole block diagram indicates as a modulator. So this is the small block diagram for generation of AM signal. This is the transmitter end antenna, this is the receiver end antenna, and here if the same carrier frequency is matched, if the amplitude is okay, no problem, but we need to synchronize the carrier frequency. And if the carrier frequency is synchronized with respect to the transmitter frequency, then we can extract the modulating signal. That derivation also we have done, how we are extracting the modulating signal, how we are providing all these things. Now the second condition comes if there is a phase difference at a carrier component which is generated in a receiver end in order to demodulate the received modulated signal. If there is a carrier change or the phase change takes place in the carrier, then what will be my output? How I will analyze if my output will not be modulating signal, but with some sort of phase difference will come into it. Okay, that we will see in this class. So let us consider the AM signal which we are going to transmit. So S suffix AM of T, A suffix C, 1 plus KA M of T and cos omega C. So this is the modulated signal I am going to transmit. Now what is this K? K is called amplitude sensitivity, which is equals to A by C, whose unit is volt inverse. Okay, so this is my AM equation. Now this AM signal I am going to transmit with the help of this transmitter part. Now when I am receiving it, ideally I am discussing, but practically when you receive the modulated signal, external noise is going to be added in it. Okay, that we will discuss later on. First we will discuss if there is a phase change in carrier which is present at the receiver end in order to demodulate the received modulated signal. Okay, now let us consider at receiver, if carrier is not synchronized properly, and suffers a phase difference, let us consider C dash of T is equals to AC cos omega CT plus phi. So that means this is the phase difference suffered by a carrier component. Now if this is my carrier, then what will be my modulating signal after the demodulation? So that will come into picture with the phase difference. Now this is my consideration. So consideration is what? Consideration is the carrier suffers a phase difference. So if a carrier suffers a phase difference, then what will be my modulating signal? So step by step we will see. Now let us consider here output of this demodulator. Let us consider it is Y of T. And then Y of T is fed to the LPF, in which it will center to the modulating frequency FM. It will remove all the harmonic components, higher frequency component, carrier frequency component, as well as the DC component will be removed from this LPF, and then we will see what is our modulating signal. Now here I will say Y of T is equals to S suffix AM of T into carrier component into C dash of T. Let us consider plus phi, which is equals to C dash of T, and here it is AC. Let us consider this is the carrier. Now if I will multiply this one with respect to AM, it is AC 1 plus KA M of T cos omega CT. Then C dash of T is AC cos omega CT plus phi. Okay. Now if you multiply this, you will get AC square 1 plus KA M of T, and this will become cos omega CT into cos omega CT plus phi. Then now this is in a form of cos A cos B. Again you have to reduce this one. So how to reduce? Let's see. So it is AC square 1 plus KA M of T whole divided by 2. 1 it will come in terms of cos of omega CT of A plus B and A minus B it will come. Okay. Now if this is done, cos of A plus B and A minus B, if I will see, cos of A plus B, I will get cos of 2 omega ct plus 5 plus cos of 5, because omega ct and omega ct will be cancelled out and only cos 5 will be the resultant value. Done. Now if you identify this thing, then this is the amplitude and these are the components. So now this is the harmonic component suffered by a phase difference phi, and this is also cos phi. So if I will again segregate this 1 plus Ka m of t whole into cos of 2 omega ct. So this is the first component plus AC square divided by 2 1 plus Ka m of t into cos phi. Okay, so now this is the additional term we are getting. So one is the harmonic component and one is the phase difference component. Now this is my y of t. Now this y of t need to be provided to the LPF so that it will suppress the DC component, harmonic component as well as the carrier frequency available at omega c or 2 omega c, as well as the DC component will suppress. And what will be my output, that also we will discuss. Now the output of LPF output of LPF. So y of t is provided to LPF. So this is the second step. Now we will get our modulating signal which suffers some phase difference, that we will see. Now when this, let us consider the output is Z of t. So Z of t is equals to, now here you can see, if I will expand this first two terms, AC square multiplied with 1, then cos 2 omega ct. So that means it consists of DC as well as the harmonic component. So that component is suppressed. Second, AC square divided by 2 Ka m of t cos 2 omega ct. That also a sideband frequency will come, but it is a higher frequency. That also it will suppress. Now next term is this one. Okay. Now next term is this one. So first AC square divided by 2 cos phi. First. Second AC square by 2 Ka m of t cos phi. That is the second term. So that means if I will multiply AC square by 2 and cos phi pass through an LPF, presence of DC component with a phase difference, it will be suppressed. So only the component what is available is AC square divided by 2 Ka m of t into cos phi. So this is the output of LPF. Because here you can consider this one as an amplitude of a particular signal, and there is a modulating signal is available whose center frequency is FM, and the low pass filter will act as the filter which will maximum frequency allowable to that particular filter is FM. So the FM is present and with the phase difference cos phi. Okay. So this is my output of modulating signal. But previous class what we have seen in our synchronous detection, if there is a no phase change, the output is AC square by 2 Ka into m of t. Again we can resolve it and we will get m of t by 2. Okay. So that is the output of an synchronous detector. But in this case we have considered that if my carrier at the receiver end suffers some phase difference, then what will be the output? What will be the effect of modulating signal with that phase difference? So this is the difference. Okay. Now this is the difference. Now here you can see, if I will resolve this, Ka is 1 by A. So here I can see AC by 2 into M of t into cos phi. Then now in place of this M of t or multiplied with an amplitude, let us consider this is a constant. AC by 2 is half of the amplitude. The amplitude is multiplied with modulating signal. Amplitude may increase, may not increase, and cos phi is the output. Now this is the output of LPF. Now this is the output of LPF. Now here the cases are arises. What cases? Cases with respect to the phase difference. First, if phi is equals to 0 degree, if phi is equals to 90 degree, or if phi is equals to 180 degree, or phi is equals to 360 degree, or phi is equals to 270 degree. That means I will take a one complete cycle. First I will measure the phi angle at 0 degree, then phi angle at 90 degree, phi angle at 180 degree, phi angle at 270 degree, and 360 degree. Okay, because these are the phase difference. Now according to this cos term, okay, according to the cos term. So first, if I will put cos of 0 degree, we will get the maximum value or the maximum modulating signal output available at output of an LPF, output of a synchronous detector. So if cos phi is equals, if phi is equals to 0, cos 0 is 1, that means my Z of t will become AC by 2 into M of t. So this is the maximum amplitude available when the phase is suffered with a 0 degree phase shift. That means there is no phase shift. So this is the original one. Next, if phi is 90 degree, okay, second phi is 90 degree. As we know that cos 90 is 0. So that means no output is available at the output of an LPF. So if 0 is multiplied to this, then Z of t will become 0. Then why I am using this phase difference? Because at the reception side the phase may not be same. It is very difficult to synchronize. So that in previous class I have discussed that designing a synchronous detector is a very tedious job. It is impossible to design the synchronous detection because there is a very complex method, or it is a complex to synchronize the phase as well as frequency of a transmitted signal carrier frequency. Okay. So now if I am using cos 180 degree, so 180 degree means minus 1, and we will get Z of t is equals to minus AC by 2 M of t. So that means this indicates what? It indicates that whenever it will suffer at 0 degree or 360 degree, we will get as a positive amplitude, positive part of a modulating signal. As you can see that AC by 2 M of t. Similarly, if it is 90 and 270 degree, there is no output because the cos 90 and cos 270 degree is 0. But if it is 180 degree, the negative amplitude of modulating signal we are going to identify. So cos 180 degree is minus 1, then output of an LPF is Z of t is minus AC by 2 M of t. Now this synchronization of the phase is very difficult. So this is why what I am saying that designing a synchronous detector is very tedious job. It is a complex circuit. As the theory it is simple, but for designing purpose it is very complex. Because if there is a phase change, we will not get our actual output. If it is a 90 degree phase shift is there with respect to the carrier, then we will get no output. If it is 180 degree phase shift is there, we will get an output but in negative quantity. But if it is 0 degree, it's okay, it will get as a positive. But if it is 90 or 270 degree, that means no output is available. If it is 0 degree or 360 degree, we will get positive output. But if it is 180 degree, we will get as a negative output. And this synchronization is very difficult to match. So the synchronous detector is very difficult to design. So the complexity is more. The synchronization is very tedious job. What I have discussed in the last class, that when I am transmitting with the help of a TV broadcasting station use a higher carrier frequency. But when we are receiving at the receiver end, which we are the users, n number of DTH services are available in different area. So those DTH services having their own frequency, own carrier frequency that need to be synchronized. Okay, and that carrier frequency may not be same as the strength what the base station is transmitting. So in that case, we can't say it is a synchronous detection. It is very tedious job. The complexity is more. Okay, so this is about the synchronous detection. Next, we will discuss about the envelope detection.